So let us start number systems. This is actually a very small topic. You can easily understand without having any prior understanding. Now, here actually we will discuss one is the conversion from decimal to any other. So in this actually the methodology is same. We will discuss. So subpart as to binary system, and the second one is to hexadecimal, to octal number system, and the C is hexadecimal. So this actually we will discuss, and then actually we will be discussing the conversion from any number system to decimal. So this is the second one we will be discussing. The next one, from binary to octal and hexadecimal, and vice versa. From octal or hexadecimal to binary. So these numbers actually we will discuss first, and if time permits, then actually we will discuss representation of or the conversion of and representation of real numbers in binary. So we will try to finish these aspects. Here the concepts are pretty simple. First one is the conversion from decimal to any other number system. Now, as I explained yesterday, so a decimal number system will use 10 different symbols to represent any number. Now if you notice, whatever may be the selection of the number system we do, we will be able to represent all the numbers. That is, from minus infinite to plus infinite, we should be able to represent any number, whatever may be the number system you select. So only thing is, the number of symbols will differ. So in decimal number system, we are using 10 different symbols. And in hexadecimal number system, we are using 16 different symbols. Now, though we use 10 symbols here and the 16 symbols here, we will be able to represent from minus infinite to plus infinite each and every number. We will be able to represent whatever may be the number system we select, right? So only thing is the length of the word or the length of the number is going to be changed. That is, if you want to represent 100 in this case, so this is going to be represented as, or actually if you want to represent 256, so in 256, so this can be represented as base number. You are using 3 different digits to represent 256, but in hexadecimal number system, we will be representing this as FF. So FF16, so this is the hexadecimal number system which you can make use. This is as if like, so F and F. So this F is nothing but 15 in our decimal number system into 16 power 0 plus 15 into 16. So power 1. So this is 15 into 16 plus 15 is nothing but 16 into 16. So this is equal to 256. Hence, you are using only two different digits to represent 256, which is decimal equivalent in decimal number system 256. It is represented with only two different digits here. But the same thing, if you want to represent in binary number system, this has to be represented as, so the same thing is 111, 111. So this is base 2 number system. Now if you notice here, actually I am using 8 different symbols or 8 different digits to represent same 256. So you are able to represent from minus infinite to plus infinite each and every number, but only thing is the number of digits what you are going to use for constructing that number will be different. So lesser the number of symbols, more the word length. So more the number of symbols available, lesser the length. So in base 16 number system you are using only 2 digits. In base 10 number system you are using 256. And in base 2 number system you are using total 8 digits. So here 8, this is 3 and this is 2. So this is the thing actually what it is differing from each and every number system. Got it? So this is a fundamental understanding we should be having it. But though it is taking many numbers or many digits to represent a single number, then actually why we are using or why we are very much interested in binary number system is a machine can understand only two different aspects. That is, suppose if you take a capacitor which is an electrical capacitor. So there are two aspects for the electrical capacitor. Either it may be charged or uncharged. So the electrical scenario can be represented as charged capacitor and uncharged capacitor. So here actually if it is charged, then actually we can treat that as 1, and if it is uncharged, then actually you can treat that as 0. That means you will be able to represent two different states. So any machine can be easily constructed if you are able to use the components which are having only two different states like this capacitor, right? So because of that nature of the machines, right, we will be constructing bigger machines with the help of the smaller machines of our capacitors like equipment, so that actually you will be able to do the mathematical operations and the logical operations which is built or which are the basic building blocks for the computers, right? So from there actually the requirement is coming. Hence, as the machines are operating with only binary numbers, we have to be worrying about this binary number system. But as we are convenient with the decimal number system, we should be able to convert to the binary versus decimal to binary. So for easier and convenient purpose actually, so these number systems, octal number system, hexadecimal number system and binary number system are interrelated to each other because of the reason that in binary number system we are using two symbols. Here octal number system we are using 8 symbols, which is 2 cube, and in hexadecimal number system we are using 4 symbols, which is 2 power 4. Hence actually these are actually interrelated to each other. So for convenient purpose at low level coding of microprocessor, this hexadecimal number system is going to be used there. So that's why actually we should be aware of the conversions from one number system to another system mathematically. Got it? So first you note down this, then actually we will see how we can convert it. Then so from decimal, let us take one number, let us say 374. So this is base 10, and this number system I will convert. So here actually first I will convert to octal or hexadecimal. So the method of converting from binary to any number system is, so whatever may be the decimal number system it is going to be. So hexadecimal number system, it is a base 16 number system. And base 16 number system, if you want to convert it, you divide this 374 with 16, which is the base. So with this 16 actually if you divide it, then actually it is going to leave a remainder which is always lesser than 16. Now what will be the remainder for 374 by 16? So this is 2 times 3 times, and then it will leave a remainder of 6. And then if you take 16 again, it goes once, and then actually it leaves a remainder of 7. And then if you take again 16, it goes 0 times and it leaves a remainder of 1. So 176 base 16 is equivalent of 374 base 10. So this is how actually you can construct a hexadecimal number system from the decimal number system, repeatedly dividing and taking the remainder and writing from bottom to top is the method. Got it? Now actually if you take the same thing, octal number system. So this is base 8. So with base 8 actually 374, if you take it, then you divide with 8. So 4 times 32, and then actually 54. Four times 32 and 54. Okay, 54, 48. This is 6. And then again 8. Then 5 times remainder 6. And again 8. 0 times remainder 5. So 566 base 8. So this is equivalent of 374 base 10. This is how you can construct it. Similarly, if you want to convert to the binary number system, then this can be divided as 374 and then divide with 2. So this is 1, 8, 7, and it leaves a remainder of 0. And then again 2. So this is 9 and 3, and it leaves a remainder of 1. And then again with 2. So this goes 4, 6, remainder of 1, and then 2, 2, 3, remainder of 0, and again 2. So this is 1, 1, remainder of 1, again with 2, 5 times with a remainder of 1, and again with 2. So this is 2 times with a remainder of 1, and again with 2. So this is 1 time with remainder of 0, and again with 2. So this is 0 times with remainder of 1. Now you can write from bottom to top. So if you want to write this as bottom to top, 10111, 10111, 0110. So this is base 2. Got it? Understood or not? Okay. So this is how actually you can convert from decimal to any other number system you want. Whatever may be the base it is exactly the same procedure you can follow. Now actually we will try to correlate these number systems. Let us see how it is going to be. See this, if I wanted to convert this number system to octal number system. Now actually I will convert this to this octal number system like this. So let me see. Here actually from binary, if you want to convert to octal number system, as the power of 2 power 3 is 8, right? So what you need to do is, you have to put a comma after every 3 digits from right to left. Like this. So that is, if you put a comma there, 110, and then after a comma, again 110, and then after that 101. So if you separate with a comma after every 3 digits, then convert or write the decimal equivalent of this number. Then, so if you notice, this is actually the 6, and this is again the 6, and this is 5. So if you notice, this is actually base 8 number system, 566, which we have constructed here. So 566 base 8 is equivalent that of 101, 110, 110. Now here actually put a comma from right to left after every 3 digits, and then try to try to write the equivalent of that number, right? So this is anyway, you know that if you are putting a comma after 3 digits, you are going to get a maximum number of 7, because actually the highest possible number with 3 digits of binary number system is 111, which is equivalent to 7. That means you can get a maximum of octal number system, not more than that. And octal number system, which is anyway subset of the decimal number system. So all the symbols what we are going to use are up to 0 to 7. Hence actually whatever you are constructing as if like it is a decimal number system is equivalent to the octal number system here. So just convert this into the normal decimal number system and put it here. So this will be octal equivalent of the same. Now the same number, if you put it a comma after 4 digits, that is, if you put a comma here, let us say 0, 1, 1, 0, then afterwards 0, 111, and then actually 1. So if you convert this number, then actually this is 0, 1, 1, 0 is a number 6, and this one 0, 111 is nothing but 7, and 1 is just 1. So 176, which is the base 16 number here. So 176 base 16 is equivalent that of 566 base 8 is equivalent that of 10111 10110, the base 2. Got it? Understood the concept? So these are actually interrelated to each other. Octal number system, hexadecimal number system, and the binary number systems are equivalent to each other. Got it? So the conversion of this number, let us say what I am saying is 110. So anyway, I am going to explain elaborately. First you note down this. See, binary to, see this. First, if you got the binary number here, you put a comma after every 3 digits from right to left. Then write the equivalent number of that 3-digit number in the decimal format like this. So 110, the equivalent of this in decimal number system is 6. Again 110, the equivalent of this in decimal number system is 6. And 101 is the equivalent that of 5. So you are just writing the decimal equivalent. Now the conversion of this number or the binary number system to decimal number system, I am going to explain now. Vishal, you understood that? See, just actually put a comma and then write the decimal equivalent of those 3 digits. That's all. And even the hexadecimal also, it will be exactly the same. Put a comma after 4 digits. Then I have to write the decimal equivalent of this number here. You just put it here. Got it? So why I am calling it as decimal equivalent is that is convenient for you. But here the decimal equivalent of this 110, whether it is base 8 or the base 10, it is always same. 6. But here actually, suppose the decimal equivalent, let us say this is 13. Then actually you cannot keep as 13 here. You have to write the symbol corresponding to 13. So in hexadecimal number system, so we are using 0 to 9, and then actually after 9, A, B, C, D, E, F. So these are the symbols actually what we are going to use for the 16 symbols there. So in these 16 symbols, A is 10 equivalent in our decimal number system. This is 11, this is 12, 13, 14 and 15. So F is 15 for us. Got it? So first you note down this. I am going to write a bigger number so that you will be able to convert it. Suppose actually if I give 1100 1010, if I put it like this, then actually what is the equivalent of this? This is a hexadecimal. So this is binary. Now convert this to base 16. If I ask you to convert this to base 16, this binary number, then actually put a comma after 4 digits. Then write the hexadecimal equivalent of this number. Hexadecimal equivalent of this number is, as you are convenient with the decimal number system, first you convert this into decimal number system. The way we convert into the decimal number system is 1010. For this actually, this is 2 power 0 and this is 2 power 1, this is 2 power 2 and this is 2 power 3. So this is 2 power 3, 2 power 2 and 2 power 1 and 2 power 0. So this is the base here. Now 2 power 0 into 0, so this is going to be 0, and 2 power 1 into 1 is 2, and then 2 power 2 into 0, again it is 0, and then 2 power 3 into 1, this is 8. So 8 plus 0 plus 2 plus 0, this is equal to 10. Now this 10 actually in hexadecimal number, we call this as A. So what you need to write it here, it is A. And again, this is 1100. The equivalent, if you exactly calculate in this manner, I think you are going to get this as 12. So 12 equivalent is C. So this is base 16 CA. Got it or not? I hope you understood this concept. From binary, you put a comma after 4 digits, write the equivalent corresponding to each and every 4 digits in the hexadecimal format like this. Any other questions? So any number system to decimal number system, if you want to convert it, right? So earlier actually, suppose any number system, let us say binary number system, if you take it. So I call, let us say 1100 base 2. Now this I wanted to convert into base 10. So if you want to convert this into base 10, the procedure is standard for whatever may be the number system it is going to be. If you want to convert into a decimal number system, the procedure is standard for all the kinds of number system. The way we have done in the previous section, saying that, so from any number, from decimal to any number system, you are just keep on dividing and writing the remainder. Even here also, from any number system to decimal, if you want to convert, it is the same procedure. That is, first you write this symbol separately like this, and then, so this is the base here. Now, for this base, you try to write 2 power 0, start with power 0, and then power 1, and then power 2, and then power 3. So like this actually you have to put it. Now, this value multiplied by this value, so that is 0 into 1, and this is 0 into 2, and this is 1 into 4, and this is 1 into 8. So put a plus in between, and then try to add all these numbers. So this is 0, and this is 0, and this is 4, and this is 8. So 8 plus 4, this is 12. So this is 12 base 10. So this number you can write as 12 base 10. Got it? This is how actually you can convert. Suppose if I give 566 base 8, now this should be 374 base 10, because actually we have proved that 374 base 10 is equal to 566. Now here we can do that. First you divide these 3 digits, 5, 6 and 6, and then start with 8 power 0 and 8 power 1 and 8 power 2. Multiply these two numbers, 6 into 1 plus 6 into 8 plus 5 into 64. So this is 6 plus 48 plus 320. So 320 plus this is 54. 320 plus 54, this is going to be 374 base 10. Got it? How we have converted this? In the similar manner, if you want to write, this is 176 base 16. Now this should be equivalent to 374 base 10, which we have proved in the previous. So here 176 again you write as 3 different digits, and then 16 power 0, 16 power 1 and 16 power 2. So here 1 into 256 plus 7 into 16 plus 6 into 1. So this is going to be 374. Got it? So this is how actually whatever may be the number system it is, so you can convert to decimal number system with the help of this standard method. Got it? Now, as you are aware of writing into the decimal number system, now let us see this one in the previous session, right? So 1100 is, and then let us say 1010. Suppose if this is the number, let us say this is the binary number system. If you want to convert this into hexadecimal number system, then you put a comma after 4 digits from the right to left. Now these 4 digits actually will give a number which is always less than 16. So maximum of 1111. So 4 ones, that is equivalent to 15. So we can calculate that. 111, if you notice, this is 1 into 2 power 0, 1 into 2 power 2 plus 1 into 2 power 3 plus 1 into 2 power 4. Now if you notice, so this is 2. So 1 into 2 power 0, this is 1, 2 power 1, 2 power 2 and 2 power 3. Yeah, this is the highest. So 1 into 2 power 3 is 1 into 8 plus 1 into 4 plus 1 into 2 plus 1 into 1. So this is 1 plus 2 plus 4 plus 8. If you notice, this is going to be 15. That means with the help of binary number system, by employing 4 different digits, you can write a maximum number of 15. So that means which is less than 16. So you can easily convert the base 16 number system. Now here, if you convert this into the base 10 first. So base 10 actually, this is 0 into 2 power 0, 1 into 2 power 1 and 0 into 2 power 2, 1 into 2 power 3. So this is 8 and this is 2. So total it is going to be 10. And here this is going to be 12. So 12 comma 16 you have to write. So 12 comma 16 you have to put it in base 16 number system. As 10 is not there in base 16 number system, the equivalent of this is A and the equivalent of this is C. So this is CA base 16 is the number. Got it? CA base 16 is equivalent to 11001010. Got it? Exactly in the opposite manner. So you can write, suppose if I give a number, let us say I give 15 or FF. So FF base 16, if you want to convert this into binary, what you need to do is you just write a binary equivalent of each and every digit with 4-digit format. That is, F is equivalent to 111. So as I explained here, 111 is nothing but 15, which is the F in hexadecimal number. Now for the second digit also, you put a comma and then I will try to the equivalent in 4-digit format. So this is going to be the binary equivalent, which you can straight away write it. So from base 16 to base 2, it is straightforward conversion. Take each and every digit, write a 4-digit binary equivalent for that each and every digit and then try to put it like this. So this is as equivalent as that of conversion from base 16 to base 2. Now base 16 to base 8 also you can write it with the help of employing the binary number system itself. What you will do is you convert each and every digit in 4-digit format of binary and then try to put a comma after every 3 digits and then write these 3 digits in the octal format. That is 3 digits, this is going to be 7 and this is again 3 digits actually. So this is going to be 7 and then this is 2 digits, 1 is 3. So 377 is the value. Got it? In base 8 format. I hope you understood. Base 16 to base 8. First you note down this, I am going to explain again. Base 16 to base 2. That is straightforward actually. So base 16, suppose I call this as AC. This is base 16. So C is equivalent to 12 in decimal number system for us and A is equivalent to 10 in our decimal number system. Now this base 16 actually, first you write A separately and C separately and write a 4-digit binary for each and every. For each digit. So C is nothing but equivalent of 12 in binary number system. So equivalent of 12 in binary number system is 1100 and equivalent of A in binary number system is 1010. Suppose actually if I give this number, let us say 2AC base 16. Now for this 2 also you have to write the equivalent in 4-digit format, or rather than if I give this number A to C in hexadecimal, I wanted to convert into the binary number system. So this is 2 and this is A. So 2 can be written in the form of 10, but you have to put it as 4-digit binary number here. For that actually 0, 0, 1, 0 you need to put it. So these leading zeros are important as you need to write always a 4-digit number. You should not use only 2 digits though it is 10 itself. Got it? Now here for A you can write as 1010. So this number which is 101000101100 is the value of A to C of hexadecimal. Got it? Understood? Okay. So any questions? So this is how actually you can convert any number system to any other number system based on this methodology. Got it? Okay. So this is straightforward and simple itself. But actually in binary number system, while writing the numbers actually you might get confused because actually you have got access to only two symbols. So even with two symbols also you will be able to represent whatever may be the bigger number it is. But only thing is it will take a lengthy. So that is, suppose the numbers are 0 and 1. So this is equivalent of 0 and this is equivalent of 1 for us. And then actually as I have used all the symbols, so the next increment is going to be the cycle. So the cycle is getting repeated 0 and then it will increment the left side digit from 0 to 1. Now again this is 0, I have got access to one more symbol 1 1. And again then actually the next symbol is 0 and here also as the carrier I need to carry here, again the symbol is going to be 0 and then I have to put a 1 here. So this is 2 and this is 3 and this is 4. Now like this actually the next number is going to be, you have to increase this number to 1 and you keep this 1 0 as it is. Now if you want to increase this number again, this is going to be 0 and it has to carry 1 here. So this is 1 1 0. Again I have got 0 here, I can increment to 1. So this is 5 and this is 6 and this is 7. And again if I increase this, this is going to be 0 and then as I have completed the cycle I need to increment the next one also. Here also I have used all the symbols. So here actually I need to put 0. Then here I need to increase as I have completed the cycle at the second position itself. Then actually I will get 0 here and then I need to increment the next one which is 100 is the binary equivalent, so which is equal to 8. So like this actually, so this is 1001 and then 1010 and then 1011 and then 1100 1101 1110 and then 111. So this is 9 and this is 10 and this is 11 and this is 12 and this is 13 and this is 14 and this is 15. So after this if you want to put it, this is going to be 100. So this is 16. As we are using only till 15 numbers, so for hexadecimal number system starting with 0 you will be using till 15 16 symbols. So it is good that if you remember all these numbers. Got it? So this is how actually you can construct it even if you forget it. Got it? So you are keep on repeating the cycle. So at first place you will complete one cycle, then increment the next one. At the second place if you complete one cycle, then you increment the next one. In the third place also if you complete one cycle, you increment the next one. So like that actually you can write any number of your own interest. Got it? Okay, so now actually if you want to convert a real number is nothing but, suppose if I wanted to convert 1.625. So 1.625 actually I wanted to convert into, so this is based on convert this into binary. Now while converting this to binary, you need to separate this 1 separately and 0.625 separately. And then for this actually you need to follow a different procedure and for this you need to follow a different procedure. Suppose I call this as 10.625. So this 10 actually you need to convert from base 10 to binary number system. So for this 10 actually you will be successively dividing this with 2. So this is 2 goes 5 times with remainder of 0 and again with 2 goes 2 times with a remainder of 1 and then 2 1 time with a remainder of 0 and 2 0 times with a remainder of 1. So this is, if you write it like this, this is going to be 1010. So 1010 is the value of decimal equivalent of 10 in binary. Now coming to the second one, this is 0.625. Now if you keep on dividing, it will keep on extend. No remainder is going to be there. So you need to adopt a different procedure here. 0.625. Now here actually you have to multiply with 2 rather than dividing with 2. So here actually we are dividing with 2. Now here we are multiplying with 2. When you multiply with 2, then actually one number actually which will come before this decimal, that is 0.625 into 2. So this is 0 and then 5 and then 2 and then 1. So 1.250 is the value. Now you have to keep this number here and then avoid this number, and then you left with 0.25. Again multiply with 2. If you multiply with 2, then this is going to be 0.5. Now this 0 needs to be kept here. And then again multiply with 2, then this is going to be 1.0. So this 1.0, you have to keep the 1 value here. So 0.625 is equivalent that of 101 after the decimal. Got it? So 10.625 base 10 is equivalent to 1010.101 base 2. So this is how actually a real number can be converted into the binary number system like this. Got it? Understood this concept? Now you can cross check it, or actually you can back verify this. See this, when you are converting this number, here actually 0 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2 plus 1 into 2 power 3. So this is the left side part. And after the decimal, so 1 into 2 power minus 1. So because actually we have done with 0 here, if you are moving on to the right side after the decimal, then actually the power is going to be the negative value. So 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3. So this is going to be, so this is left side anyway, we know that this is going to be 10 and then plus, and the right side actually 1 by 2 plus 1 by 8. So 1 by 2 is 0.5 and 1 by 8 is 1.125. Then actually the sum of this is 10.625, which is the decimal equivalent. So this is how actually a real number can be converted into, a real binary number can be converted into decimal real number like this. Got it? Understood the concept? Any questions on this? So this is how actually you convert the real numbers also. And then representation of negative numbers of binary. Now here, usually to represent a number in binary, right? So we will be specifically allotting certain digits for that particular number. So the standard convention is you will be allotting 1 byte to represent one number. But this 1 byte actually, 1 byte is equivalent to 8 bits. And 1 bit is either 0 or 1. So this is actually, it will occupy one particular position. Now usually if 1 byte is allocated, there are actually 8 different places that are allocated. This is 1, 2, 3, 4, 5, 6, 7 and 8. So like this actually 8 different places are allocated to represent 1 byte. In 1 byte actually if I notice, so here actually the minimum value is 0, 0, 0, 0, 0, 0, 0. So this is the minimum value, and the maximum value I can make use is 1, 1, 1, 1, 1, 1, 1, 1. So here actually this is the maximum number and this is the minimum number. I can represent with the help of these 8 positions. Now these 8 positions, if you notice, this is the decimal equivalent of 0 and this is the decimal equivalent of, this is going to be, so 255. So this is 2 power 0 and 2 power 1. So this is actually, if you multiply, if you add all these things, so this is going to be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. Now the sum of all these things actually, so this is 1 plus 2 plus so this is going to be 255. Got it? So this is 255. That means you can represent a maximum of 255 and you can represent a minimum of 0 with the help of these 8 bits. Got it? So now actually if you want to increase the size or actually if you want to represent a bigger number, then actually you can increase these positions. So usually in our computer programming, at least in C language actually, we will be using 4 bytes to represent an integer number. So 4 bytes means 4 into 8. So this is 32 bits actually are allocated to represent an integer number in our standard C programming. So 32 bits meaning the maximum value actually this 255 is nothing but 2 power 8 minus 1, where this is equivalent to 1 byte. Right? So this is equivalent to 1 byte. That means if you are allocating 32 different positions to represent a number, the maximum number you can represent there is 2 power 32 minus 1. So this is the maximum possible number of integer. But if you want to represent a bigger number than this, then actually one option is you have to allocate more number of bytes, or actually if you are trying to do a calculation with a number which is more than this number in C programming, it will lead to a wrong result, or actually it will go to a fatal error. Why? Because actually it won't understand what is that number is going to be, because you have used a number which is greater than 2 power 32 minus 1. Got it? Because there is a limitation there. So there in C programming we allocated only 4 bytes, but actually nowadays actually we are allocating even 8 bytes, or actually even the 12 bytes or the 16 bytes also are allocated to represent or to do with the calculations of bigger numbers. So for now actually there is one more integer number called long. So long is also an integer number but allocated with 8 bytes. So 8 bytes mean 8 into 8. So this is 8 into 8, 64 bits are allocated. So if 64 bits are allocated, the maximum possible number you can represent is 2 power 64 minus 1 is the highest possible number which you can represent with the declaration of long integer. Got it? So for integer it is 4 bytes and for long integer it is going to be 8 bytes. So that is 1 byte is nothing but 8 different bits. So here actually even the internet speed also will say 2 Mbps or 10 Mbps. There actually 10 Mbps. So M means mega. So 10 Mbps. So this is mega and this is bits, not bytes. So megabits per second. So 10 megabits per second. That means 10 power 6 bits per second. So when we are calculating internet speed, right? So like actually if I say that 10 Mbps connection, then actually in 1 second maximum it can download 10 power 6 bits as a data or as an information, or it can upload 10 power 6 bits in 1 second. So that is the usual internet speed actually what we are using in nowadays, right? So there actually the important thing is this B is nothing but the bits, not the bytes. Got it? 100 Mbps means 100 megabits per second. 100 into 10 power 6 bits in 1 second. So that is the transmission rate that is happening there. Got it? So here actually the data is stored in computers in the form of these bits, and the transfer rate of the data is going to be measured in terms of the bits itself. So this binary number system is important for us. Got it? Any questions on this? So here now the complexity comes here. Now if it is a positive integer number, if you notice actually whatever the numbers I have written here, these are all only the positive numbers. So the minimum number I can represent here, it is 0, and the maximum number I can represent with 1 byte is 255. But what if I wanted to represent -1 or -10? Then there is a deficiency that is coming. Here in this format of allocating the bits, I won't be able to represent a negative number. So then so we have decided to use this leading symbol as only for the sign. So this leading symbol is used for the sign representing 0 for positive and 1 for negative. So this is how a signed integer is represented. So this leading bit is allocated only for the sign, and then remaining 7 bits are going to be used to store the number. Now suppose if I say that this is 2 power 7, so because 1 bit got reduced now, so 2 power 7 minus 1 is nothing but 127. Yeah, so 127 is the highest possible number I can represent with the help of this. But this 127 is plus or minus. Plus or minus means I can represent a range from minus 127 to plus 127. So this is the maximum possible value I can represent with the help of this 8 bits. So here minus to plus is the range. Earlier 0 to 256. Now it is going to be minus 127 to plus 127. Got it? So this is the leading digit is allocated for the sign. Now for the calculation purpose or for the arithmetic purpose, right? So it is easy to represent, or it is required to represent these signed integers in a different formats. So there are 2 other formats that are available. Those formats are 1's complement and 2's complement. So 1's complement meaning, so the opposite of that is suppose 1100. So this is a decimal number system of 12. Or if I represent with 4 different bits, then if I wanted to store a number, then maximum I can store is 100, keeping this as the sign. That means this can be represented as -4. And the 1's complement of that is, so this is -4. Suppose if I call this as 0, then this is going to be +4. Now the 1's complement of that is, you make a negation of this. Negation means opposite. So 0 becomes 1, 0 becomes 1, and 1 becomes 0, and 0 becomes 1. So this 1011 is equivalent that of -4. So that's what is called as the 1's complement. No, Pankaj. So this digit is dedicatedly allocated only for the sign. If it is 1, then the remaining digits are used to represent a number as usual. So that is, we have got only 7 different bits now. So 7 different bits you can make use to represent a number. So with a range of 2 power 7 minus 1, which is equal to 127. As this bit got allocated for the sign, if you keep this as +1, then this is going to be a negative number of -1, minus of the number whatever you represent here. And if it is going to be 0, then the plus of the number whatever you are going to represent with the remaining 7 bits. So this is dedicatedly for the sign either to represent as a negative or positive, and the remaining digits are dedicatedly to represent the magnitude of the number. So that maximum magnitude what you can get it is from 127, negative value to positive value. Got it? Understood? So there are 2 different methods to represent negative numbers. So those representations are, one is the 1's complement and the 2's complement. 1's complement is, this is opposite, that is 0 becomes 1 and 1 becomes 0, exactly opposite to that. Now if it is 0, then this is going to become positive, this is going to become 1. So this is a negative number and this is a positive number. 1's complement is opposite of it. So +4, if it is represented as 0, 1, 0, 0, minus 4 can be represented as 1011. So that is a minus 4. Don't try to think that actually this number can be directly written as 1 into 2 power 0 and 1 into 2 power 1. It represents only plus 3. But actually this is a minus 4 value. So don't get confused. This is one method to represent a negative number. And there is another method also, 2's complement. 2's complement is nothing but adding 1 to the 1's complement. So if I add plus 1 to this, whatever the number you are going to get it, that is the 2's complement. Here actually, while representing this number, there are two different main disadvantages. One disadvantage is, here actually, you are reducing the range of the number what you can represent. Earlier actually you tried representing till 255. But actually now we have got only the range till 127. So the range got reduced. This is one disadvantage. And another disadvantage is, so the zero value. So zero value is, so 0, 0, 0, 0, 0. If you keep this as all zeros, then this is as if like plus 0. Because actually the leading symbol is 0. This represents the sign, this is plus 0. Now actually if I take the complement of it, then actually if I keep this 1, then 1, 0, 0. So this will represent minus 0. Now here actually, in our decimal number system, plus 0 is equal to minus 0, equal to 0. But here actually, we have allocated two different places for 0 itself. This is another disadvantage. So 0, this is plus 0 and this is minus 0. Plus 0 and minus 0 are one and the same. But we are using two different places to represent this 0. So this is one disadvantage. And another disadvantage is, with the help of this number system, addition of the numbers is a little complicated for the circuit design purpose. Hence actual people thought, and if there are any other ways of representing the negative numbers, so that I can easily add or I can easily subtract. So that kind of operations. So there are actually two methods actually people came up. Those are 1's complement and 2's complement, which you can make use to represent the negative number. Got it? So there actually we tried avoiding, with the help of 2's complement, we tried avoiding two different places for the 0 and the easiness for the circuit design purpose, which is the adder circuits. So with those advantages actually we came up with the 2's complement is the most popular signed number representations. Got it? So that's why actually the 2's complement is, suppose if I take with 4 different bits. First you note down this, I am going to erase it and then try to explain it. Then so let us consider a 4-bit number. Signed number. Let us say if I wanted to represent plus 4. So plus can be represented as 0, 1, 0, 0. So this is plus 4 for us. Now actually to represent the negative number, so I can do 1's complement. 1's complement is 1, 0, 1, 1. So this is 1's complement. This is minus 4. And if you notice, these two digits are allocated only for the sign. The negative number, if you try to correlate, this is not 100 as if like 4 here, right? So this is actually another way of representing the negative number. There are 3 different ways of representing the negative number. The first one is keep the number as is and keep the leading digit only for the sign. That is one method. And that method is having inherent disadvantages in the circuit design purpose. So we started another method. That method is 1's complement. Now in the 1's complement method, suppose here actually if I add these two, 0 plus 1 is 1 and 0 plus 1 is 1 and 1 plus 0 is 1 and 0 plus 1 is 1. Now if you notice, so the complement of this, so here actually this is 1 1 1 1 1. Now this is going to be negative 0. Sorry. So first actually we take the 2's complement. 2's complement actually take the negation of it and then actually add a plus 1 to it. So if you add a plus 1, then actually this is going to be, so 1 plus 1 is 0. 1 plus 1 is 0 and then 0 plus 1 is 1 plus 1 again 0 and then again 0 and 0. Just a minute. So this is 0 1 0 0. 1's complement of this is writing the opposite of it. Opposite is 1 0 1 1. Now the 2's complement is, so you need to add for the 1's complement. 1's complement, add plus 1. So for this 1's complement, if I add 1, then actually the resultant is going to be 1 plus 1 is 1 0. 1 plus 1 is 1 0. So keep 0 here and keep a carry. 1 plus 1 is again 1 0. So keep 0 here and then actually keep a carry here. And then this is 1 plus 0 is 1 and then this is going to be 1. So 1 1 0 0 is the 2's complement of this plus 4. So this is representing minus 4. Now actually if I add plus 4 and minus 4 together, it has to result into 0. Now plus 4 is 0 1 0 0. So this is plus 4. Now if you add these two, 0 and 0, and 1 plus 1 is 1 0 and with a carry of 1, and 1 plus 1 is 1 0 and with a carry of 1. So this leading carrier you can ignore because actually we are trying to work with only the 4 digits. So if you notice, plus 4 and minus 4, if we add it together, it is resulting into 0. Now actually our mathematical operations are satisfied with the help of this 2's complement, where the 2's complement is defined as the opposite of the number, which is we call as the 1's complement, and then add plus 1 to it. Whatever the number is going to result in, that will be the 2's complement of it. Now if you notice, the fundamental purpose of representing the first digit as the sign, so plus is represented with 0 and minus is represented with 1. Got it? So this is the 2's complement. So this is the most popular method, signed number representation purpose. Got it? Yeah, you can note down this. Okay. So with this actually, so this is actually signed number representation. So with this actually I would like to stop the class for today. In the next class actually I am going to deal with the memory components and the computer components. See this, if you take any number, let us say if you take 3, plus 3 can be represented with the help of 4 different digits is plus 3. First you keep 0 as the leading digit and then 1 1 is the 3. So as you need to use 4 different digits, 0 1 1. So this is representing plus 3, which is allocated 4 different digits, and the leading digit represents the sign which is plus for us. Now here the 2's complement of this is, first you write to represent minus 3, what you need to do is 1's complement plus 1. So 1's complement of this is writing opposite digits for each and every one. That is 1 becomes 0, 1 becomes 0, and 0 becomes 1, and 0 becomes 1. So this is 1's complement. And for this actually you need to add 1 so that you will get 2's complement. So 0 plus 1 is 1, 0 plus 0, 0 plus 0 is 0, and 1 plus 0 is 1, and 1 plus 0 is 1. So 1 1 0 1 is the 2's complement of 0 0 1 1, which we represent in mathematics as minus 3, which is the 2's complement of this plus 3. Now, so mathematically plus 3 and minus 3 should be equal to 0 if you add these two together. Now here actually, if you add this one and this one, it should result into 0. So 0, 0, 1, 1 and add with 1, 1, 0, 1. Now if you add these two, 1 plus 1 is 1, 0 and with a carry of 1 and 1, 1 is again 1, 0 with a carry of 1 and 1 plus 1 is again 1, 0 with a carry of 1 and 1 plus 1 is again 0 with a carry of 1. Now here actually, though we are getting a leading carrier here, we will ignore this. Why we will ignore this is, we are trying to make use of only 4 digits to represent the number. So whatever the leading carrier that is coming out, which you can safely ignore it, and then if you notice, this is plus 3 and this is minus 3 and this is the result of 0. So the arithmetic operation of addition is getting satisfied here, right? So this is how actually you can make use the 2's complement to represent a negative number. This is the most popular method and this is widely used across the design purpose. Got it? And the main advantage of this is you can make use of an adder to add these numbers. So this is the main advantage. So with the help of the adders itself, you will be able to subtract the numbers. So by applying 2's complement and adding to it. Got it? Okay. So actually we will take one more example. Suppose actually if I add plus 3 and minus 1, it should result in plus 2, right? So plus 3 and minus 1. So what I will do is, plus 3 I can represent as 0, 0, 1, 1. And minus 1 I can represent as, minus 1 is nothing but, so plus 1, 2's complement you need to write it. For plus 1, it is 0, 0, 0, 1 is the plus 1 and the 1's complement of it is 1, 1, 1, 0 and 2's complement of this is 1, 1, 1, 1. So this is the 2's complement of minus 1. So this is the minus 1. So all ones. So now actually if I put it here, 1, 1, 1, 1, now this is going to be 1 plus 1 is 1, 0 and this is 1. So 1 plus 1 plus 1. So this is actually 1, 0 plus 1, 1. So this is 1 and then a carrier of 1. 1 plus 1 is 1, 0 and then again 1. 1 plus 1 is 1, 0 and a leading carrier you can ignore it. Then if you notice, the resultant is 2. So as we have calculated plus 3 minus 1, it should be equal to plus 2. And here also, if you notice, whatever we have got is 0, 0, 1, 0, which is equivalent to 2. So this is how actually you can do a 2's complement and add it to the number for the subtraction purpose, rather than adder and subtractor design. So the main conclusion here it is, usually when we are designing the circuits, right? So more or less actually what we will do is, we will try to generate one circuit and try to make use of that circuit to do maximum number of operations. So we fundamentally get actually two different operations. One is the addition and another is the subtraction. So what we will do is, we will just design an adder which will add the two different numbers and then we will make use of those adder itself to do the subtraction also, this manner. Because actually even if you notice, I found the 1's complement and then I added it again. In both the cases actually 1 plus 1 equal to 2. If you add it with the help of adder, it is going to be 2 and then 1 minus 1 has to result into 0. For that what I will do? I will do a 1's complement and then add 1, which we call as the 2's complement and add it to the original number. It will again do the same result. That means you are making use of the adder circuit itself even to do the subtraction also. See this, as I said, right, 2's complement by definition it was defined as 1's complement plus 1. 1's complement meaning writing opposite digits for each digit of the number. That is 1's complement. If we add 1 to that, that's what we call as the 2's complement, which we will use in binary number system to represent the negative number. Got it? Yeah. For that actually, you can take any negative number for the purpose. Now actually, see this here, plus 3 is 0, 0, 1, 1 is the plus 3. Now if I wanted to find out the negative value, which we call as the 2's complement of plus 3, is first write opposite digits. 1 becomes 0, 1 becomes 0, 0 becomes 1 and 0 becomes 1. Now I add 1. So this is 1's complement. This is 1's complement and then you add plus 1, which we call as the 2's complement. So this is 2's complement. 2's complement is nothing but the negative representation of plus 3. So this is how actually minus 3 is calculated. So this is representing minus 3 and this is representing plus 3 in binary number system. So for the analysis purpose, I am just proving that plus 3 and minus 3, if I add it together, it should result into 0, which I have done it here. Plus 3 and minus 3, in decimal number system, we know that it is going to be 0. The same thing is proved here. 0011 is nothing but the plus 3 and 1101 is the negative value which was represented in the form of the 2's complement 1101, which I have added it here. These two addition results into 0 as satisfied by the decimal number system. Even in the binary number system also, this representation of 2's complement method for the signed digits is valid, proving this plus 3 and minus 3 is equal to 0. Understood, Sanjay? Okay. So yeah, so that's all for today. In the next class actually, I am going to deal with the logic gates and if possible the memory. Got it? Yeah, that's all for today. Thank you. Good night.